Good morning. Welcome to the fourth lecture of this week as part of this ongoing online course on sustainable architecture, and we have been discussing about indoor air quality in this week. So, in the previous lecture we discussed about the VOC compounds, and towards the end of previous lecture we discussed about the controllability of lighting and thermal comfort systems. So, today we will start with how to design the indoor environment for thermal comfort and visual comfort, which is appropriate thermal environment and appropriate optimized optimally lit indoor environment. Now, when we talk about lighting, the emphasis here is to have as much daylight as possible and totally cut off the need for artificial lighting, especially in the daytime. So, we start with thermal comfort design. Now, when we have to design building interiors for thermal comfort, we would take help, or we would take the benchmark as the code, which is ASHRAE standard 55. So, the intent is to provide a comfortable thermal environment, and it is required in order to promote the occupant productivity and overall well-being. How do we do that? We design the indoor environment, indoor space to meet the requirements which are given as part of ASHRAE standard 55. Those are the conditions which are required, which are specified as thermal comfort conditions for human occupancy. To ensure that the design of HVAC, heating, ventilation and air conditioning systems plus the building envelope will be done in order to meet with the requirements. One option is that, which is the prescriptive approach. If we are not doing that, the other way is to demonstrate this performance by using the local standard also. So, instead of ASHRAE 55, we could go ahead and use an equivalent standard, local standard. For example, in our case also we go back to ASHRAE standard 55. So, for us it does not make much of the difference. However, in several other countries, especially Europe, where they have their own thermal comfort requirements and the standards, they may be used. So, when we are talking about the thermal comfort design, and we have already seen these different parameters which affect the thermal comfort. So, we know that there are environmental parameters and then there are personal parameters. So, we have to take care of all these parameters. We have to take care of the air temperature, the radiant temperature, the air speed and the humidity as part of the environmental parameters, and as personal parameters we have to take care of the clothing insulation and the metabolic rate. Now, metabolic rate will be dependent upon the activity or the purpose of the space. So, if it is an office space, certain metabolic rate will be assumed, and also the clothing will be assumed, because when people go to office they are clad in a particular kind of attire. So, these two will be assumed, while the rest of these environmental parameters, they will be designed for thermal comfort using HVAC. Now, we can design the system in such a manner that these environmental parameters are met. We have desired amount of humidity, we have ample amount of air speed, and we are also able to manage the air temperature and the radiant temperature. But how do we know whether the system is performing as it was designed? So, is there a way to understand whether building occupants are comfortable with the given design? So, the next very important criteria is the thermal comfort verification. So, the next very important criteria is thermal comfort verification. Now, the intent here is to provide for the assessment of building occupants' thermal comfort over time. As a design intent, we have already designed the HVAC system and the building considering that thermal comfort will be ensured for all the building's occupants. However, it may not really be delivered as it was intended. So, what needs to be done is we would provide a permanent monitoring system to ensure that the building performance meets the desired comfort criteria as determined by the thermal comfort design, which we just saw as the previous slide. How would that be done? One, conducting the thermal comfort surveys with building occupants within a period of 6 to 18 months after occupancy. So, as soon as the building has been put up for use, it is occupied, it is up and running, the building occupants will be surveyed for thermal comfort. From the thermal comfort survey, the results will indicate whether thermal comfort is being achieved or not, whether what was intended through the design has been implemented or on ground. So, we would really verify whether thermal comfort has been achieved or not. If not, then once the survey has been conducted, we would identify the corrective course of action, which would be indicated by the survey results. So, whatever the survey results indicate, if more than 20% of the occupants are dissatisfied, then a corrective course of action needs to be taken and it needs to be implemented. Also, we have to include the measurement of relevant environmental variables in problem areas in accordance with ASHRAE standard 55. So, it is not just thermal comfort, but we would also be monitoring couple of other environment variables besides those for thermal comfort, for example, carbon dioxide. So, all of this would form a part of thermal comfort design and verification, and after verification the corrective course of action will be taken. So, this was about thermal comfort and its design. The next very important part is daylighting. Now, the intent here is to bring in daylight to maximum floor area of the building. The intent is to provide the connectivity between the interior and the exterior spaces to achieve visual delight to occupants. So, it is not just about bringing in light, but it is also about the visual comfort, because when we are connected to outdoors, human beings inherently they feel more comfortable when they are directly connected to the outside. Even when there is sufficient artificial light which is provided inside the building, a connection with outdoors, greenery, plants is always going to bring in a greater sense of visual comfort. So, not only does bringing in daylight results in energy savings and demand reduction, because then the need for artificial lighting is offset, it also reduces the cooling load, because the efficacy of daylight is significantly higher than any other form of electrical lighting. So, it produces less heat as compared to the amount of light. So, more daylight inside implies less requirement for artificial lighting. So, not only does it reduce the energy consumption, besides that it is also required for building occupants visual comfort and well-being. The occupants feel better and their productivity increases when they work in daylit areas. So, this is proven by the research, and that is what is intended in sustainable buildings and green buildings. Now, how do we ensure that there is sufficient daylight and how much is enough? So, to define that, several terminologies have been used and there are several definitions which are available. The two most common which are used in green buildings are, one is daylight factor and the other one is UDI, which is called the useful daylight illuminance. Couple of years back, daylight factor was the most commonly used terminology. However, gradually UDI is becoming more popular. So, daylight factor is actually the ratio of the light level inside a structure indoors to the light level outside the structure, that is outdoors. So, daylight factor is just a ratio, while UDI is defined as the annual occurrence of daylight between 100 lux to 200 lux on a work plane. Now, whenever we are talking about the daylight design, we are looking at the amount of luminance, the daylight present on a work plane height. It is not on the floor, it is not on the ceiling, but it is on the working plane, at the height of the working plane. So, UDI is the annual occurrence of daylight between 100 lux to 2000 lux, and this range is actually the most useful for the occupants. It is glare free most of the time. Of course, glare depends upon a lot of other parameters as well, but between this range it is mostly the glare free light, and it totally eliminates the need for artificial lighting. So, how can we bring in daylighting? If we look at the architectural design approaches, the passive design approaches, there are several features of architecture which can be incorporated. First of all, the building form itself. So, certain building forms encourage bringing in of daylight, for example, U-shaped or stepped back or courtyard for that matter. So, wherever we have atriums or courtyards which are open to sky, they bring in a lot of light to the building interiors. So, that is through building form itself. In addition to that, we can incorporate several elements. For example, the skylight. The skylight would light up a lot of interior area directly. We have windows, we have light shelves, which is a very interesting concept which is being used these days. So, light shelf will allow reflection of the light, the daylight, to the ceiling, which will be painted light and with a reflective color or material, so that it penetrates the light deeper into the interior space. So, in addition to that, we might also use reflectors. There are louvers and blinds which can be used to direct the daylight capture. There are special types of glasses also, where they have within the glass itself, they have inbuilt prisms to diffuse the light. We also have the artificial light wells, where in deeper areas the light from the roof can actually be brought in by the light tubes. So, such elements are available in plenty, and they can be made use of while designing green buildings or sustainable buildings. In addition to daylight factor and UDI, we have to consider several other parameters as well. One very important is the angle of obstruction. What is the angle of obstruction? So, from a window, at the center of this window, if we make an angle with the nearest obstruction, the maximum height of the obstruction, so this angle which is formed is called the angle of obstruction. Some green building rating systems also talk about the upper limits of this obstruction. In case the obstruction is greater than a certain number, the window is not considered for daylighting calculations or for bringing in the outdoor views, outside views. So, in IGBC, this limit has been set as 70 degrees. So, if it is higher than 70 degrees, then this window will not be considered for bringing in the daylight or to offer the views. So, it is not just the daylight or the amount of daylight, but it is also the amount of views which are available, which needs to be considered, which will be considered with the help of angle of obstruction. Now, when we are designing the windows for bringing in daylight, besides the design of windows, one very important criteria is the selection of glass. So, which glass will be selected? Now, there is a kind of balance which needs to be stricken. For heat ingress, for controlling the amount of heat which is coming in through the windows, we suggest that the U value of the glass should be lower and the SHGC of the glass should also be lower. Now, if you look at the kind of glasses which are available in the market, which have a low U value and a lower SHGC for a warm climate we are discussing, most of such glasses would be coated with metallic coating. They would either be hard coat or soft coat, but they would often have coating. Now, this coating reduces the amount of visible light which is penetrated through the glass. So, while we are reducing the amount of heat gain through the building, at the same time we are also reducing the amount of daylight which will be penetrated through the glass window. So, when we are selecting the glass, we would be talking about a comparison of both the VLT and SHGC for different types of glazings, and select the one which will balance the heat ingress and also the daylight penetration simultaneously. Besides this comparison between the visible component and the SHGC, we will also take into account the window wall ratio. So, if it is a smaller window, maybe a clearer glass can be provided, while if it is a large window, a glass with low VLT may also bring in sufficient amount of light. So, there are two things to be compared, VLT with SHGC and WWR in combination with VLT. A product of WWR and VLT is called effective aperture. So, we have to look at effective aperture, what is the window wall ratio, and we have to look at the combination of VLT and SHGC and choose the glass appropriately. That determines to a large extent the design of daylighting in a building. Once we have done that, we will calculate the daylight factor. So, daylight factor, as we have already discussed, is the ratio of light level inside a structure to the light level outside the structure. Simply EI divided by EO, which is outside, and taking it as a percentage. Now, the EI, when we are talking the amount of luminance, amount of light which is available inside, has multiple components. So, it has three distinct components. One is the direct light from a patch of the sky which is visible at a point considered. So, it is known as the sky component of the light which is going to come indoors. That is one. Second is the externally reflected component. So, suppose we have a building right opposite our window which is painted in light colors. So, the sunlight might actually be falling onto that window and the reflected component might be received inside the building which is being considered, which is being studied. This is called the externally reflected component. So, we have to take into account that also. So, at times there may not be sufficient amount of sky component available, but there might be a lot of externally reflected component which might be available. The third very important significant component is IRC, or internally reflected component. Now, this internally reflected component is because of the reflections from the indoor surfaces, the interior surfaces. So, the light may be entering only through the window, but then it gets reflected to the ceiling and it further penetrates inside, which is what we were just seeing when we discussed about the concept of light shelf. So, when we have a light shelf and it is painted with a reflective coating on the top, the light is then reflected to the ceiling and then coming in. This is going to be considered as internally reflected component. A combination of all these three will give us the illuminance inside. So, when we are talking about the daylight factor, we would be talking about the amount of illuminance which is available inside versus the amount of light which is available outside, both being considered in lux here. On an average, a 2% daylight factor is considered reasonable. It is the threshold, minimum threshold, and if we have a 2% daylight factor, the space is considered to be reasonably daylit. Let us quickly look at an example calculation here. So, if we have to calculate the amount of light which is available in a kitchen, considering that there is a recommended daylight factor of 2% for a kitchen, and if we have to calculate the illuminance given that there is 5000 lux available outside as the external illuminance. So, if we consider 2% daylight factor and we taking it as a percentage, we just multiply the daylight factor with external illuminance, and since it is a percentage, we divide it by 100 and we get the internal illuminance which is being targeted here. However, this 2% daylight factor has to be achieved with the help of window design, the selection of glass, the design of the window, the size of the window. So, when we are talking about compliance as per ECBC, UDI has now replaced the daylight factor, and in UDI as per ECBC, 90% of the areas must be potentially daylit. Currently, daylight factor has been replaced by UDI, useful daylight illuminance, and the criteria varies. So, the minimum compliance is for majority of the codes. So, if we are talking about ECBC here, at least 40% of the area should be daylit for 90% of the time in an year with the minimum prescribed UDI. So, if we are looking at the minimum mandatory requirement, 40% to 50% of the area should be daylit. If we are looking at securing credits or earning points on the basis of the green building rating systems, for example IGBC or LEED, then it goes on to say that at least 75% of the floor area for any given space must be sufficiently daylit as per the UDI requirement or higher. So, we have to look at how much of the area is being sufficiently daylit, not just at a particular moment in time, but throughout the year, at least 90% of the times in an year. To calculate that as per ECBC, now to show the compliance, there are two ways in which the compliance for daylight can be shown. One is we can show the compliance manually, or we can go for daylighting simulation tools. So, if we are going ahead with the daylighting simulation method, we have to follow certain guidelines. First, the measurements whatever we are taking should be measured at a work plane height of 0.8 meter above the finished floor, which is what we have already discussed. Also, the daylight should be calculated only for the spaces, all the spaces enclosed by permanent internal partitions. They may be opaque, translucent or transparent, whatever, which have a height greater than or equal to 2 meter from the finished floor. The third is the period of analysis. It shall be fixed for 8 hours per day, any time between 8 am to 5 pm. A total of resulting in 2920 hours for all buildings except for schools. For schools, it should be analyzed for 7 hours per day, anytime between 7 am to 3 pm. Also, the useful daylight shall be measured on a point by point grid value. It should not be only one point in a space, but it should be point by point grid values, and that will be then averaged out. And then the fenestration shall be modeled with actual VLT, which is being considered in the building. Considering all these, the simulation, daylighting simulation may be carried out. If we look at the ECBC requirement which are given for manual calculations, you would find this table 4.3, which gives us the DEF values or daylight extent factors for the daylit area. Now, depending upon the type of the window, the latitude of the place where these windows are being designed, and for different orientations, along with the projection factors of the shading which has been provided. and also the selection of glass depending upon the VLT less than 0.3 and greater than 0.3. The DEF values are given in this table. So, for each window separately the DEF will be calculated or found out from this table as per ECBC. Once we have found out the DEF, we will then go on to calculate the amount of daylight which will be available in an area. Now, this has to be calculated in both the dimensions. So, we will calculate the amount of floor area will be daylit first for perpendicular direction. So, for example, we have a room where the window is available. So, in the direction which is perpendicular to the fenestration, here the length of this area which will be daylit is calculated by multiplying the DEF by the head height of the fenestration or till an opaque partition is present, whichever comes earlier. So, multiplying the DEF with the head of the window, we can calculate the perpendicular distance up to which the daylight will be available. The second is in the direction which is parallel to the window, at least 1 meter on both the sides of the window, the horizontal expanse of the window daylit area will be calculated or it will be determined. In case there is a partition available within this distance, so whatever is less will be considered. Now, this area is the daylit area because of this window. So, for any given plan, this daylit area can be manually calculated and the compliance criteria remains the same, that at least 40% of the floor area should be daylit for 90% times of the year. So, if you look at these two plans, the same plan has been analyzed for daylighting, one with the help of a software and the other one with manual calculations. So, here this is the plan, this is an open plan, and based upon the amount of windows which are available, the daylit area with the help of software has been calculated, shown here, while with the help of manual calculations following the DEF and the procedure given in ECBC, this is the amount of daylit area. Now, the percentage of this area will be calculated and the compliance be shown. So, with the help of the daylight simulation software which is embedded as part of Revit here, the compliance has been shown for 2 times on September 21. So, for 9 AM and 3 PM, and then we can see that the area which is passing the threshold limit is exceeding 75%, which is the minimum requirement if you want to comply with LEED. So, if it has crossed 75%, this building design is eligible for earning a credit for daylight compliance. So, when we have to show the daylight compliance, each window in the building will be considered and the floor area which will be sufficiently daylit will be calculated and the compliance be shown. So, we will stop here. Here we have completed our discussions about how to design a building and interior space for thermal comfort as well as daylight, and we have also seen the compliance approaches, how to show the compliance and how to earn credits for this given criteria. Thank you so much for being with us today. We will go on and discuss about certain other aspects of indoor environment quality for interiors as with regards to interiors in the last lecture of this week tomorrow. So, see you then. Thank you for being with us.